It's always going to be the case that really focusing on the practice tests is going to help you as much as anything to prepare for the tests in our class. I never try to put something on a test that isn't just like something on a practice test. So if you can do all the problems on this practice test, you should be able to do all the problems on the test. This graph I probably stole from Google Images before I learned how to make graphs on Desmos. And all the points aren't labeled, but I think it's easy enough to figure out what the points are as we go to answer these questions. So I didn't update this graph, but it should be fine. The first three parts of question one just want me to find function values, and that's just the y-coordinates of points that have that specific x value. If I look at 0 on the x-axis, there's 2 points that are on the line that goes through 0 on the x-axis. The point 0, 1 that's marked with an open circle, and the origin 0, 0 that's marked with a closed circle. When I'm trying to evaluate a function from a graph, I need to take the y-coordinate of the closed circle. So part A, f of 0, is going to be the 0, which is the y-coordinate of the point that has an x-coordinate of 0 that has a closed circle as opposed to the open circle. For f of 1, there's only one point marked above 1 on the x-axis, and that looks to me, that's the point 1, 2. It's marked with a closed circle, so that's considered part of the function. And I'm just going to write f of 1 equals to 2. And lastly, f of negative 2, there's just one point on the graph that has an x-coordinate of negative 2. And that point appears to be the point negative 2, positive 1. So f of negative 2 is positive 1. You should have been able to, if I asked you to find f of 2, just in case something like that comes on the test, if I look at 2 on the x-axis, there are 2 points marked. There's the point 2 comma 1 and the point 2 comma negative 1. Each point that's marked with an x-coordinate of 2 is marked with an open circle, and open circles aren't considered parts of the function or points on the function. F of 2 would be a DNE. It does not exist, or it's undefined at 2. There's no point on the graph that's marked with a solid circle that has an x-coordinate of 2. Now we get to do some limits. The first limits are the left-hand limit at 0, the right-hand limit at 0, and the two-sided limit at 0. For the left-hand limit at 0, I'm looking at the graph to the left of the point that has x equal to 0. I'm trying to find the y-coordinate of the point that the graph connects to, and the y-coordinate is going to be 1. The left-hand limit is going to be 1. For the right-hand limit, I'm looking for the portion of the graph that's to the right of 0 on the x-axis, and trying to find the y-coordinate there. These two halves of the graph meet up at the same point, so the left and the right-hand limit are the same. It's when the left half of the graph at a value of x and the right half of the graph at a value of x don't meet at the same point that you get different numbers. But here, this hole right here is going to be, the y-coordinate of the hole is going to be the answer to both parts D and E. Both the left and the right-hand limits are 1. And when the left-hand limit and the right-hand limit are the same number, the two-sided limit is that number. So the answer to part F is going to be 1 as well. And then the last part, the left and the right-hand limit at 2. The left-hand limit at 2 is focusing on this portion of the graph. It's the portions of the graph to the left of 2. And the portion of the graph to the left of 2 meets up with the graph at the point 2, 1. The left-hand limit is going to be the y-coordinate of the point 2, 1, so it's going to be 1. So for my left-hand limit, I look to the portion of the graph to the left of the value here, x of 1, of 2, and get y of 1. For the right-hand limit, I'm looking at the portion of the graph to the right of 2 and the point that it flows out of that has an x-coordinate of 2, and that has a y of -1. The right-hand limit is going to be at -1. And this jump in the graph between the 0.21 and the 0.2 negative 1 causes the left and the right hand limits to be different. It makes the two-sided limit at 2 to not exist. So wholes are okay. All the limits, the left-hand limit and the right-hand limit will be the same. Jumps, the left-hand limit and the right-hand limit will be different. And when the left-hand limit and the right-hand limit are different, then the two-sided limit, the limit without the little minus or plus sign, doesn't exist. Next are a couple limits at infinities. And limits at infinities, if there's a dashed horizontal line, it's going to be the y-coordinate of that dashed horizontal line. Sometimes we did graphs that had two dashed horizontal lines, and the right-hand limit, or the limit at positive infinity, was different than the limit at negative infinity. In this case, since there's only one horizontal line, both the limit at positive infinity and the limit at negative infinity is going to be the y-coordinate of that line, which apparently is y equal to 2. So off on the far right edge of the x-axis, there's a positive infinity, and the graph is supposed to get close to this dashed line. It's supposed to tell me what the limit is. The limit as I go off to positive infinity is the y-coordinate of that line, and the y-coordinate of that line is 2. The negative direction on the x-axis is to the left of the origin, and to the left of the origin, this is still going towards the same dashed line that has a y-coordinate of positive 2. So both the limit at positive infinity and negative infinity are just going to be 2. For the next graph, it's also asking me to find a limit at infinity, but the graph isn't stabilizing. It's either shooting up or shooting down. And the limit as x goes to positive infinity, since this graph is going up, and up is the positive y direction, the graph is going to the top of the y-axis, and the limit as x goes to positive infinity, we're going to say is positive infinity because the graph is going up. This is the negative x direction, and in the negative x direction, the graph is going down as opposed to up. I don't have a dashed horizontal line, so the limit doesn't really exist. It's not a number that I can write down. It has to be an infinity. And in the negative direction, the graph is going down, so the limit's going to be negative infinity. Now we have a few limits doing algebra. Generally, I always should just plug the number in, and if I get a nice defined number, that number is going to be what the limit is. If I get a fraction that's 0 over 0, then the limit likely exists, but I probably need to do some algebra. So for problem 4a, I'm just going to take the number 2, plug it in for each of the x's. I get 9. And since that's a well-defined number, I'd say that's what the answer is. The limit for this function is 9. And you can simply just write the number 9, or you can write the problem and then 9. The next two problems are the limits of fractions not at infinity. I'm going to get 0 over 0 if I plug the numbers in. I should plug the number in and verify. In this case, I should plug in x equal to negative 2 when I'm going to find this limit and verify. I get 0 over 0, but I know that's going to happen on my test. And when you get 0 over 0, there's algebra that we need to do for the limit. And in this case, the algebra is factoring and canceling. I'm going to pretend that I plugged in negative 2 and got 0 over 0. Well, heck, let me just plug it in. If I plug in negative 2, I get negative 2 squared plus 5 times negative 2 plus 6 over negative 2 squared plus 8 times negative 2 plus 12. This is what I should do, but if I don't do it, it's not the end of the world. The numerator is going to be 4 minus 10 plus 6. The denominator is going to be 4 minus 16 plus 12. And if I do that, I get 0 over 0. If you get 0 over 0, the limit likely exists, but you just need to do algebra. And the algebra for this particular limit is factoring and canceling. So again, hopefully your factoring skills for just easy factoring like this isn't so bad. To factor x squared plus 5x plus 6, I'm going to create two parentheses. I'm going to lead the parentheses with a couple of x's, and the numbers I put in my parentheses need to multiply to 6 and add to 5, and that's going to be 2 and 3. So the numerator is going to factor into an x plus 2 times an x plus 3. Of course, I could have written x plus 3 times x plus 2. That would have been equally okay. For the denominator, the numbers I end my parentheses with need to multiply to 12 and add to 8, and it's going to be 2 and 6. The denominator factors into x plus 2 times x plus 6 because the numbers 2 and 6, if you multiply them, you get 12. If you add them, you get 8. Now I can cancel out the 2's and get the limit as x approaches negative 2 of x plus 3 over x plus 6. Now I can stop writing the word limit because I'm going to plug the number in, the number negative 2 in, and get negative 2 plus 3 over negative 2 plus 6. The numerator simplifies to be 1. The denominator simplifies to be 4. That's a well-defined number. That's what the limit is. The answer to 4b is the number 1/4. You know, if you want to write the answer with the problem, fine, but just the number is fine. And on Canvas, you know, doing a Canvas test, I would only write the number. This would be ridiculous to type on Canvas. C is another fraction limit not at infinity. Technically, I should be plugging in the value that's provided to me, but realistically, I don't really have to. I'm doing autofocus right now, so it's going to make it so you can't see what I'm writing. It's not such a big deal because I'm just showing you that I'm going to get 0 over 0 when I plug in 49 for the x's, because I get 7 minus 7 over 49 minus 49, and that's 0 over 0. This is the ugly computation. To do this limit, when I have this funky square root set up, I have to multiply by the conjugate of the numerator, which is the numerator with its sign changed. And I have to do that to both the numerator and the denominator. So I'm going to multiply the numerator by the square root of x plus 7, and I'm going to multiply the denominator by the square root of x plus 7. When I do the multiplying, when I start simplifying, I'm not going to FOIL out the denominator, but I will the numerator. So in the numerator, I need to FOIL. The firsts are the square root of x times the square root of x. And when I multiplied two identical square roots, like square root of x times square root of x, I just get the radicand, or what's under one of the square roots without the square root symbol itself. And then outers are the square root of x times 7, which is plus 7 square root of x. Inners are minus 7 times the square root of x, that's minus 7 square root of x. And lasts, minus 7 times 7, that's minus 49. And these problems are set up so that the outers and inners will cancel, and the numerator will cancel with one of the factors in the denominator if I don't multiply the denominator out. The numerator simplifies to be x minus 49, and I haven't touched the denominator because I know how this kind of problem works, which you should by now too. Now I can cancel the x minus 49s. I need to rewrite the problem, but I can't write it without a fraction. If you cancel the entire numerator of a fraction, you still need to leave a 1 behind for that numerator. Now I can plug in 49 and not get 0 over 0. I'm going to get what the limit is. So this is going to be the square root of 49 plus 7, which is now going to be 1 over 7 plus 7. And my answer is just 1 over 14. If you do enough of these, you can kind of predict what the answer is going to be ahead of time. If you write down an answer and don't show this calculus on the test, you're just going to lose all points. I'm really grading the work more so than the answer. So if you can figure out a way to get the answer, that's fine in terms of checking, but you need to show the work to get credit. When we have limits at infinity for fractions, I need to search all the x terms and find the highest power of x term. Here, both the numerator and the denominator have an x squared term as the highest power, as their highest power. So the very highest power of x term in this problem is x squared. And when we did limits at infinity for fractions, plugging in the infinity was essentially worthless. I might have done it once in a video, maybe twice, but it wasn't productive. What we need to do for these fraction limits at infinity is multiply the entire numerator as well as the entire denominator by 1 over the highest power of x that occurs anywhere in the problem. And then clear this multiplication. In the numerator, I'm going to multiply 1 over x squared by the 8x squared, and I'm going to multiply the 1 over x squared by the 1. When I show my work on on my answer key, this is usually my first step that I'm writing right now. Usually I don't show that step because I can kind of do that step in my head. So now I'm going to go into cancel mode that I multiplied each term in the problem by 1 over x squared. First piece in the numerator, the x squareds cancel. I don't get a fraction for that piece. I just get the 1 times 8 that's uncanceled, and 1 times 8 is going to be written as 8. No canceling happens when I multiply 1 over x squared times 1, but anything times 1 is itself. So I'm going to get 1 over x squared to end off my numerator. Starting in the denominator, I'm going to cancel the x squareds and be left with 1 times 2. The first piece of my denominator won't have a fraction. The second piece of my denominator, this x squared will cancel with that x. That x will go away completely. This x squared is going to have 1x left over when I do the canceling. So I'm left with 1 over x times 4, and that's what 4 over x is. Now I can plug the infinities in. Once I get each of the x's in the denominator of a fraction, I can plug the infinity in. And when I plug the infinity in, I stop writing the limit symbol. So I get 8 plus 1 over infinity squared divided by 2 plus 4 over infinity. The fractions that have infinity in the denominator, whether it's an infinity or an infinity squared, are equivalent to 0. So I'm going to rewrite this as 8 plus 0 over 2 plus 0. That comes out to 8 over 2. And my answer to 5a is just the number 4. Again, I know what the answer to 5a is before I do any algebra. So I'm grading the work more so than the answer. If you write down an answer without any work, you're going to lose full credit. I want to see some work, whether it's this just a little bit, and you skip that line, that's okay. But if I don't see any work, for correct answers, you're not going to get credit. Another limit at infinity, 5b, is for a fraction. And similarly, x squared is the highest power of x. To find the limit at infinity of any fraction, I scan the numerator and I scan the denominator. I look for the very highest power of x that occurs on either level. In this case, it's the x squared that's buried in the denominator. And I multiply by 1 over that power of x in both the numerator and the denominator. Again, this is a step that I normally skip. I usually go straight to this mode, multiplying each term in the numerator as well as each term in the denominator by that, in this case, 1 over x squared. When I start off the numerator, this x squared and that x cancels. The x goes away completely. The x squared only cancels down to an x. I'm left with 1 over x times 5. And 1 over x times 5 simplifies to be 5 over x. The next piece of my numerator doesn't do any canceling. I'm just going to write 4 over x squared for the result of that multiplication. Moving down to the denominator, The x squareds cancel in my first multiplication. I'm just left with 1 times 2, which is 2, and I don't get a fraction there. The middle of my denominator, the x squared and the x cancel each other. This x goes away completely. This x squared just cancels down to an x. And I'm just left with 1 over x after the minus sign. And lastly, this doesn't cancel, and that multiplies out to 2 over x squared. So now I can plug in the infinities and get 5 over infinity minus 4 over infinity squared in the numerator, and 2 minus 1 over infinity plus 2 over infinity squared in the denominator. All the fractions that have an infinity or infinity squared in the denominator are going to be reduced to 0. So I get 0 minus 0 over 2 minus 0 plus 0. That gives me 0 over 2, and fractions with 0 in the numerator are equal to 0. My answer to 5b is just the number 0. Again, you can write the answer with the problem or just write the number. 0 is the number here for the answer. Notice that when I plugged in infinity, I stopped writing the word limit. That's custom. You always write the word, that's just customary or correct. You always write the word limit until you actually plug the value in. And once you plug the value in, you stop writing the word limit. The next problems give us a graph and ask me for the informal reasons and the points where the graph is not continuous. And this is not particularly hard. A graph isn't continuous if there's an asymptote, a hole, or a jump. I didn't show any asymptotes here, so I'm just looking for holes and jumps. The values of x in problem 6 where the function is not continuous are at x equal -3. So for my answer, where are the points where the function isn't continuous? It's not continuous at x equal to -3. And the informal reason is there's a jump in the graph at x equal -3. So I'm just going to say for my answers, I'm going to write down the values of x's where there's an asymptote, a jump, or a hole. And then I'm going to find the informal reason. Here, the informal reason the graph is not continuous or the function is discontinuous at x equal -3 is there's a jump there. Moving over to the first hole I see, that hole is at the point 1, 2. So the next value where the graph is not continuous is x equal to 1. And there's a hole at x equal 1. But in terms of holes, it's either an unplugged hole or a plugged hole. And at x equal to 1, there isn't a point marked on the graph with a solid circle that has an x coordinate of 1. So there's a hole and the function is undefined at x equal to 1 because there isn't a corresponding point that has a black circle or solid circle, depending on the color, I guess, with an x coordinate of 1. The next hole I see is at x equal to 4. That's the last value where the graph is not continuous, so there's also a hole at x equal to 4. But at 4, there's a corresponding point marked in whatever color that is that makes the function defined. So there's a hole, but the function is defined at x equal to 4. The only other thing I could have thrown on here is a vertical asymptote. Usually don't do those. I like showing the holes and the jumps more so than the asymptotes. The asymptotes come up when we do the domain from an equation. I mean the continuity from an equation. So that's problem 6. Problem 7 asks the same question. Find the values where the function isn't continuous or it is discontinuous equivalently, but it gives me a fraction. And to find the values of x that make a fraction not continuous, the graph of a fraction not continuous, you set the denominator equal to 0. And the values of x that make the denominator equal to 0, they make vertical asymptotes if their factors don't cancel with the numerator. They make holes if their factors cancel with the numerator. To find the values of x where the fractions graph would have breaks in it, you set the denominator equal to 0. Because the denominator here has a square, I need to solve by factoring. And again, this is just easy factoring, so hopefully your factoring skills are good enough that without me explaining how to factor that you could factor it down to that. Once I get it factored, I can tell whether I'm going to have a whole or not. If I had a factor of x plus 3, which would cancel with the numerator, then the value of x that factor produces would give me a whole. Since neither of the factors will cancel with the numerator, both the values of x that I get from my algebra here are going to give me vertical asymptotes. So I'm going to take the x plus 5 factor, set it equal to 0. That's going to give me one of the values of x where the graph is not continuous. It's going to be x equal to negative 5. It's going to be a vertical asymptote there because the x plus 5 factor doesn't cancel with the numerator. Similarly, when I take the factor of x minus 1 and set it equal to 0, I get another place where the graph isn't continuous. It's at x equal to 1. And because x minus 1 doesn't cancel with the numerator, I also get a vertical asymptote there. So the graph is not continuous at x equal negative 5 and x equal to 1. And there's a vertical asymptote at both x equal negative 5 and x equal to 1. I would only get a whole if the denominator would cancel with the numerator. 7b asks the same question but gives me the equation of a line or the equation of a polynomial. And there's no algebra. The function is continuous everywhere for this problem. And so there's no algebra I can do. To state the values where the function is not continuous, it's continuous everywhere, so there's no values of x that I can say. When I'm given a polynomial and I'm asked to find the values of x where the graph isn't continuous, we just say it's continuous everywhere. So that's kind of the first half of the chapter. That's kind of sections 1.1, 1.2, and 1.3. And so I'm going to make a part 2 video that covers sections 1.4 and 1.5. And let me pause this video and then kind of move into the second half of the chapter.